So let's start with Assembly and Packaging Technology. In German, it's Aufbau- und Verbindungstechnik. And in the summer semester 2020, we will have an electronic lecture. That's a little unusual for me, so I hope you will become accustomed to it as well as I do. Okay. First of all, let's make a small summary what to expect. And there are three aspects which are very important. One is the technologies of assembly and packaging. So we need some housing for the devices. The devices must be mounted to some substrate. And in order to bring both together, we need interconnection technologies like these solder balls we see here. Of course, all electronic systems are made from some matter. In that case, it's called material. And so material science and its influences on the properties of assembly and packaging are really important. And I expect that you have some pre-knowledge on materials, but there will be lots of informations which I will treat implicitly. So you don't need to have all the background. We will explain the materials in detail. In the end, when we have materials and when we have technologies to build something from, we need also good designs. And the design of assembly and packaging must be a proper electrical design. On the other hand, we know every PC needs a cooler for the processor, so thermal design is important. And especially in automotive applications, also mechanics and reliability are of utmost importance. Okay, in order to show you the table of contents of that lecture, first of all, we will start with the packaging concepts for electronic systems. So to give you a certain overview, the next thing is we will explain the several levels of integration, so-called first level and second level. And there are especially housing technologies, and these houses, as I said, will be mounted on certain substrates. For the housing, there are quite many technologies, and we must learn about these. It's similar with the substrates. We have organic substrates or polymer substrates. We have ceramics-based substrates, we have thin film-based substrates, and all of these have their special applications and their special features. And in the end, also, we must be able to compare these substrates and to select proper substrates. Bringing the parts together, for the major parts, it's called assembly technologies, and for electrical interconnection, it's called interconnection technology. So assembly comprises soldering, gluing technologies, and special other bonding technologies we will see in detail. On the other hand, for the interconnection, maybe most of you knew about wire bonding or about flip chip bonding. And again, here a comparison is important. For a proper design, we must learn about the main effects of packaging on electrical signals. We must learn about thermal management, how heat develops and how we get rid of heat in electronic systems. And then finally, we will see mechanical problems which have an effect on mechanical design. Very important is In the exercises, we will go through exercise questions, and in the end, I will expect that you will be able to solve a certain design task. That design task will be explained a little later, and such design tasks, as you can find them in the lecture notes, also will be subject of your exam you will have probably in August or in September. Okay, now let's proceed. And why do we have certain packaging concepts for electronic systems? Some of you possibly heard about the so-called Moore's Law, and Gordon Moore was manager at Intel, and in 1965 he wrote a famous article, Cramming More Components onto Integrated Circuits. And in that article he stated that before 1965 the number of circuits or transistors on an integrated circuit had doubled every 1.5 years. Okay, that law over a time of 6 years, that correlation was extrapolated. And here we can see this Moore's Law until, let's say, here I got the data until some years ago, and we can see the different generations of processors. Moore was an Intel guy, so it's mostly Intel, but also AMD. Here we see the 8080, which was one of the first 8-bitters by Intel. Then we have a 68000, 16-bitter by Motorola. 8286, 16-bitter by Intel around the year 1980 or 82 or so. And in that way, we had a straight line in that semi-logarithmic scale. Now, while we started with very small number, let's say here, 100 transistors, here presently, 2020, we expect 10 to the power of 10 transistors on one chip. Okay, from 10 to the power of 2 to 10 to the power of 10, so it is an increase by a factor of 100 million. And of course, that could only be achieved by, first of all, making transistors significantly smaller, going down from many micrometer size to maybe 10 nanometer size. On the other hand, it was also important to make larger and larger wafers. So while in the beginning they started with 2-inch, which is 50 millimeter, now they do the processing for VLSI with 12-inch wafers. And in that way, processors could be more and more powerful, and the price level could be maintained more or less, yes? Okay, but in the end, electronics do not just consist of processors. We have passive devices. For instance, we have chip resistors or chip capacitors, which go down to sizes something like 1 millimeter by 0.5 millimeter. These small devices, they are often kept in some as a bulk material, and such devices, then they are called chicken food. So passive devices also became smaller and smaller, and they are important. On the other hand, also having more transistors requires more and more IOs. We also have new interconnection technologies like flip chip with diameters of individual balls going down to 30 micrometers. Now let's have a look at the devices. While with a so-called quad float pack device, as we see it here on the top, for instance with 100 or with 200 IOs, we have a edge length of 22 millimeter. That posed some problems when we were addressing significantly increased numbers of IOs. For instance, doubling the number of IOs would mean maybe devices with a size of 33 millimeter square then. And in that way, even individual devices would be extremely large. The solution for that was the so-called ball grid array. That means all the IOs which are first in a peripheral fashion are now sorted in a grid, and in that way a similar device only has an edge length of 13 millimeter. These devices could be made smaller and smaller, and if you are able that the device is only 20% by area larger than the chip, it is called a so-called chip scale package. In the end, people had more and more ingenious ideas, and so chips could be stacked inside the package. That requires, of course, internal interconnections. And so in that way, not only the size was reduced, we had a trend towards first two-dimensional and then three-dimensional arrangement. And in that way, the complexity of electronic systems increased significantly. This information here was given by Infineon company. Okay, now reducing sizes is not what we need alone. If we look at modern embedded systems, what else do we have? I mentioned the passives, but we also have analog circuitry, RF circuitry, for instance, a Bluetooth circuit or an instrumentation amplifier taking up a small signal and increasing it, amplifying it. We have high voltages, typically up to 1200 volts for high power. We are now talking about chips which can carry between 200 and 500 amps for a single chip. And of course, for the IMTech people, sensors and actuators are of utmost importance. Another thing is biochips, so bringing electronics in contact with human bodies, for instance, or inside human bodies, you need special assembly and packaging. So there is a lot of diversification, and that diversification is important to create modern electronic systems, and in that way the requirements to assembly and packaging also increased. We have more complex systems, they have more versatile capabilities, and on the other hand, the computational power was tremendously increased. Okay, what is important now for assembly and packaging? AMP not only has to deal with smaller and smaller structure sizes, but it also has to deal with combining very different technologies. On the other hand, if you are able just to solve all these problems with CMOS technology, then you can integrate it on one chip, but that's not possible. For the passives, we have some barium titanate. For the high voltage power, we have some vertical device. An IC is a lateral device. For RF, we need gallium arsenide. So we see it's impossible to put it all on one chip. So we need assembly and packaging. And in that way, we can compare two technology lines. One is monolithic integration, and the second is so-called hybrid integration. Hybrid integration means we have different device technologies and integrate them in a system. For instance, in an embedded system. Okay. The trend in IC is more Moore, so smaller, more devices, and so on. In hybrid integration, we call it more than Moore. Not only making smaller, but making it more versatile. On a monolithic IC, especially on a CMOS, the flexibility of using different transistor technologies is low. It's limited. On the other hand, by hybrid integration, for instance, soldering it together, you can combine almost anything, so you are flexible. On the other hand, you can never make a circuit smaller than when you integrate it on one chip. And in that way, of course, the so-called packaging density, that means how many transistors per cubic millimeter, is of course not so good in hybrid integration as it is in monolithic IC. On the other hand, the development time for a circuit nowadays, it can be relatively fast for a monolithic IC, for instance, at least if it's only for a part of that circuit. Of course, if it's very complex, or the generation of a new processor at Intel takes rather years than months. But before prototyping, so it's in the order of months. Also, of course, for hybrid integration, you need some electronics engineering, and also it takes months. Design changes in hybrid integration can often be accomplished quite fast. On the other hand, if you have an IC, which you create on wafer, you must have a proper time slot in the wafer fab, and that can take months until you have a new wafer which requires many masks. Also, in that case, you make a completely new wafer. On the other hand, when you do hybrid integration, maybe you only change some parts of your circuitry. The costs per part, when you make only very few circuits, are extremely high in monolithic ICs. Yes, you have extremely expensive processes. Maybe you need 60 masks and 60 process steps. And if you only need one wafer and you get out a few thousand devices, you have possibly hundreds or thousands of dollars for an individual chip. On the other hand, the costs per part in very large series are extremely low. We are talking about here then about cent or so per square millimeter, or several cent. So in the end, it can be extremely cheap, especially on 12-inch wafers. The costs per part when you do hybrid integration is not so much depending on how many parts you have. You buy standard devices, they are somewhat cheaper when you buy larger amounts, but in the end, I would say in both cases it's medium costs. On the other side, the development costs of, for instance, a printed circuit-based circuit are medium high, but for a monolithic IC, which is state of the art, you have very high development costs. Here for new processor generation, we talk about billions of dollars for each processor. Okay, now let's switch to assembly and packaging. I was working for a company who do acceleration sensors. You possibly know why we need acceleration sensors, mainly in automotive applications. The first sensor was a sensor for crash detection, and that was what my colleagues designed in 1992. It was a device that was in a metal housing. Also, the fixture at that time, we thought it must be very well defined in order to precisely monitor and record the crash pulse we have, and then to release or fire the airbag. On the other hand, the second reason why we had a metal housing was that a metal housing is what we call hermetic, and so the chip is very well protected in here. And then the package was simplified. What you can also see at that time, we had a barcode, but after a few years, all of that was changed over from a device which has pins and which has a metal housing to a plastic housing, which is a so-called surface-mounted device. So we have no longer holes in the printed wiring board. We can just mount it on a printed wiring board. We found out that that is sufficient for crash detection. There were other innovations, like having this QR code here instead of a barcode. And in that way, that was a development. And still we must say, now such sensors for acceleration measurement still are made in a very similar way as they were done over 20 years ago. Another device which is very important also in automotive applications is so-called Hall sensor. A Hall sensor is a sensor where we have a current here and we measure a voltage here. On the other hand, the old-fashioned Hall sensor was a metal, and later on that concept was transferred to silicon. But Hall sensors, they worked, but they had many disadvantages. For instance, Hall sensors are very sensitive against temperature, because the mobility of carriers in silicon is very much depending on the temperature. In that way, people in IC companies thought about how to improve such sensors, and so on-chip instrumentation was added. So besides the Hall element, we have a compensation circuit. We have even a signal processor. After the signal is digitized, the signal is processed, and after the processing, the signal is reconverted again to analog signal. So let's say magnetic field of 0 to 100 millitesla is proportional to a voltage of 0 to 5 volt. That chip was made in CMOS technology, and now for automotive applications, for instance, for detection of some switch on an engine, a temperature of 170 degrees centigrade was required, and the accuracy which is desired in that case is maybe in the 1% region. Such a device is made on a lead frame. That's such a copper structure here. The chip is mounted. What we can see not so good is it is wire bonded, and finally it is encapsulated with a polymer material. And such a device is very cost sensitive. Also, it is very complex. The costs are significantly below €1 or $1 per device. I would say we are significantly below such costs. Another example of such monolithically integrated system is a humidity sensor. So in many applications, also in smartphones, we would like to know what is the humidity in the environment. Is it moist? Is it dry air we have here? And we want to know the temperature, so we want to have some information about the climate. To that purpose, we need a special housing. And that housing must have a cavity where the sensitive structure is open, so air can come to that structure, and the sensor can feel what the temperature is, and is it 10% humidity or is it 50% humidity, and so on. Again, the architecture of such a device is similar to the Hall sensor. It's just a different transducer concept we have here. But what was also important is that we need very low failure rates for such devices. For instance, here people talk about failure rates of 1 to maybe 10 fit. And 1 fit is 1 failure in 10 to the power of 9 hours per sample, times sample. So that means you can take 1 billion devices and test them for 1 hour, or you take 1,000 samples and test them for 1 million hours, or you take 1 million samples and test them for 1,000 hours. In the end, you get a number of failures, and in that case, it would be, for instance, 1 to 10 failures you have with that testing effort. So fit rate is very low failure rate, but in the end, it is somehow state of the art. Maybe complex processors go up to 100 fit or so. So you have a guess what such devices must tolerate, and tolerate means, for instance, environments up to 125 degrees centigrade. For such IC packages, we have seen we had for the molded packages, which have plastic housing here. We have very simple packages with few IOs going to the ball grid array and then to the chip scale packages. And In the end, the trend went towards system in package. That means not only one chip, but we can have several chips of different technologies. And that's a so-called roadmap. And roadmaps are always important in assembly and packaging, or generally for people who produce electronic circuits, because the customers must be able to plan their equipment, they must be able to plan their design tools for more and more complex circuitry. Okay, that's another hybrid concept. That's a so-called multi-chip module. So often, when you need the same IC, like for instance, some RAM or a similar device, then you can increase either the chip size or you can just take more. And having many such IC of the same type, it's a so-called multi-chip module. That is an early case. Modern multi-chip modules do not have their chips side by side, but as we have already seen, modern multi-chip modules can have stacked chips. So now I already mentioned first level and second level packaging. I could show it to you on a sensor concept. For instance, we have an acceleration sensor or a rotary rate sensor. That's an image by Bosch company, and on the inside it has some micro-mechanical structure. As we can see, it's so-called surface micromachining structure, and here we have some movable interdigital electrodes, and these change the capacitance of the device, and from the capacitance we can see, for instance, if there is a force on that device. That means, do we have an acceleration or deceleration or some rotary rate which leads to centrifugal forces. Okay, such a device, again, when you produce MEMS, it is extremely hard to combine it with CMOS technology. In that case, we have a two-chip design in one package. That's a so-called first-level package. That's a package as we, for instance, solder it on a printed wiring board. So here we have the MEMS, and here we have the ASIC, application-specific integrated circuit. So that's made specially to drive that MEMS and to have the instrumentation for that MEMS. On the other hand, such a first-level device can be soldered onto a printed wiring board. And again, that printed wiring board is in a housing. That housing, again, has also some mechanical features. For instance, it has these ears here with holes, so we can screw it to some structure in a car, for instance. And here we have a socket for an interconnector, so we can plug in a cable, and so it is easy and cheap to mount that device. So acceleration sensors are by far not as complex as rotary rate sensors, so the complete system is very cheap, very much smaller. Also, this helps Bosch to satisfy different customers. For instance, the car's electronic architecture in a Renault car is somewhat different than from a Toyota, for instance, or from a Volkswagen. So What would be very expensive to make an ASIC, especially for Toyota, Renault, Peugeot, and so on. So the Bosch, they want to keep with their standard ASIC to produce it, and their standard MEMS to produce it in extremely high series numbers. On the other hand, the adaptation to the individual car type is much easier when you do it on the second level and just design a somewhat different printed wiring board, and maybe use a little other programming here on a EEPROM or something like that. And in that way, the second level is used to adapt it to the individual customer. For instance, also Peugeot has other sockets for the interconnector than Volkswagen. So in that way, a company like Bosch can, on one side, keep effects of large series, and on the other hand, can adapt flexible to customers' demands. Assembly and packaging comprises more. That's a so-called anti-brake locking system, and I don't know if all of you know how it works. Everybody knows what it is for. So if you have a wheel in a car and that wheel blocks, especially if it's a front wheel, you can no longer steer the car, but it slides into the direction which you initially had. So no more curves. With an anti-brake locking system, you avoid locking of a brake and of a wheel, and so you can still steer and go around something which is, for instance, lying or standing on the road, and at the same time slowing down your car. How does that work? Anti-brake locking system interacts with the hydraulic brake of your car, and to that purpose the hydraulic pressure must be taken away from your wheel. So the wheel is blocked by hydraulic pressure and friction, and if you take away the pressure, the wheel is released, and that must happen between 20 and 100 times per second, so you need a quite speedy control circuit, and you need coils which actuate some actuator, and that actuator opens or closes valves. So every wheel has two valves, one to open, one to close, and in that way each wheel can be controlled individually. And to that purpose, we need coils which are able to generate a large magnetic field, and that magnetic field works on some magnetic valves. And in that way, we can build up such a system. So an anti-brake locking system always consists of electronic parts, first level packaging, second level packaging, and electromagnetic components. So all of these must be integrated, and again, that's the business of assembly and packaging. Also important are multifunctional devices. Again, that's something from automotive applications. For instance, here, that was a circuit which measures the manifold pressure in a car. Manifold pressure gives you information how many air is taken up by the combustion engine, and the more air it takes, the more power it can develop. That's in that way you need to attach it to some pipe which is some flexible hose or such a thing. On the other hand, you need electrical interconnections, and so it gives you output what is the pressure. Again, for the manifold, you need information how the throttle, what the position of the throttle is. That again can be done with a sensor. In that case, it's not an analog but a digital sensor. And again, here we have a combination of printed wiring board and some injection molded part, and again we have an interconnector here. Modern devices are more and more complex. In that way, for instance, we do not have a printed wiring board, but here this housing itself carries some of the conductors, and that's a so-called molded interconnect device. Another example is integration of strain gauges. Again, here on the level of assembly and packaging, we produced sensors where we can take up signals. These are not on-chip sensors, but on substrate sensors. And here, for instance, we have an interdigital capacitor, and that capacitor is sensitive against temperature, against humidity, but you can also use it with proper calibration as a stress sensor, how large a force is. On the other hand, even here you need structures which are which